This is the second video in a series where I cover everything you need to know to build a GPS receiver from scratch. In the previous video, I gave an overview of the series and what I hope we'll achieve. In this video, I'll introduce three concepts. The first is the correlation of two signals. The second is the cross-correlation of two signals. And the third is the autocorrelation of a single signal. These concepts are used extensively in GPS receivers. Amongst other things, they're used to decode signals from satellites and to track them as they move across the sky. So it's really important that we understand them. If you're already familiar with these concepts, feel free to skip to the next video. Otherwise, let's get started with correlation. Here we have two signals, two values that change over time. The horizontal axis is time, and the vertical axis is amplitude. The correlation of two signals like these is a measure of their similarity. That's a bit abstract though, so let's see if we can build an intuition. These signals look quite similar. When one is positive, the other is positive, and when one is negative, the other is negative. They also seem to change at around the same points in time. These signals are almost the same, so they would have a positive correlation. Here we have another two signals, but this time, when one is positive, the other is negative, and vice versa. However, they still seem to change around the same points in time. They're almost opposites of each other, so they would have a negative correlation. And finally, these two signals don't look similar at all. There doesn't seem to be a relationship between their signs, and they change at different points in time. They're nothing alike, so they would have a correlation near zero. Now that we've built a bit of an intuition about correlation, we can introduce the formal definition. If we have two signals, f of t and g of t, their correlation is defined as the integral with respect to time of their product from negative infinity to positive infinity. At the risk of oversimplifying integration, this is kind of like taking every point in time between negative infinity and positive infinity, multiplying the values of the signals at those times, and summing the results. At this point you might be asking, won't that be an infinitely large number? Well, if we're not careful it will be. However, we typically assume that signals go to zero when we're far from the origin, like this. That means when we're far from the origin, their product will be zero, it won't contribute anything to the correlation, and we'll be left with a finite number. There's one other category of signals that we care about, and that's periodic signals, like these. They don't go to zero far from the origin, they repeat forever. So our previous definition of correlation could result in an infinitely large number. How can we avoid this? Well, instead of integrating from negative infinity to positive infinity, we integrate over one repetition of the signals, one period, like this. Assuming the signals are well behaved, this sets an upper bound on their correlation. We can express this mathematically. If we have two periodic signals, f of t and g of t, their correlation is defined as the integral with respect to time of their product from some arbitrary point in time t0 to t0 plus t, where t is their period. This is the same as the previous definition. We've just changed the limits of the integral so it only covers one period. It's also important to note that there's nothing stopping you from integrating over multiple periods, like this. Each period is the same as the last, so it has the same correlation, and the overall result is scaled proportionally. In other words, if you integrate over two periods, the correlation will be twice as big. 3 periods, 3 times as big. We can express this mathematically too. On the left-hand side of this expression, you can see we're calculating the correlation over n periods. On the right-hand side, we're calculating it over one period, but we're multiplying that by n. This property will be useful to us in the next video. So how do these definitions match the intuition that we built earlier? Well, if two signals are almost the same, we'd expect them to have the same sign at most points in time. So their product will usually be positive, and they'll sum to a positive correlation. If two signals are almost opposites, we'd expect them to have opposite signs at most points in time. So their product will usually be negative, and they'll sum to a negative correlation. And finally, if two signals are completely different, sometimes their product will be positive, sometimes it'll be negative, and overall they'll cancel each other out to give a correlation near zero. So the definition and our intuition seem to agree. So that was correlation. Next, let's build on our understanding of correlation to define cross-correlation. We'll start with another example. What do you think is the correlation of these two signals? They look very similar, but they're not aligned in time. When one is positive, the other is 0, so their product is always 0, and their correlation is 0. However, if we were able to shift one in time so that there was some overlap, then they would have a non-zero correlation. And that raises an interesting question. How far should we shift the signal to maximize the correlation? Let's try plotting it. At the top here, we have the same graph as before, and at the bottom, we have a graph of correlation versus shift distance. As we start shifting the signal, there's still no overlap, so the correlation remains 0. However, if we continue, and they eventually overlap, then the correlation increases. It continues increasing until the signals overlap perfectly, at which point it's at its maximum. After that, the signals overlap less and less, so the correlation decreases until it hits 0 again. This graph that we've plotted, down the bottom here, is known as the cross-correlation of the signals, and it's useful for finding the shifts that result in the maximum or minimum correlation. In this case, you saw that the maximum correlation occurred when the signals overlapped perfectly. The final topic we'll discuss in this video is autocorrelation. The autocorrelation of a signal is its cross-correlation with itself. Let's look at another example. This is the same layout as before. The top graph is our signal, and the bottom graph shows correlation versus shift distance. At the moment, the signal and its copy overlap perfectly, so there's a spike in the correlation. You can see this if I shift the signal slightly. If you think about it, the signal and its copy will always overlap perfectly if there's no shift, so there'll always be a spike at the origin in the autocorrelation graph. As we continue to shift the signal, the graph tells us how similar the signal is to shifted versions of itself. If it's a periodic signal, like this one, the autocorrelation function will also be periodic as the signal repeats. There are 4 things that you should take away from this video. The first is an intuition for the concept of correlation. If 2 signals are almost the same, their correlation will be positive. If they're almost opposites, it'll be negative, and if they're not similar at all, it'll be near 0. Second is the definition of correlation, both for signals that go to 0 far from the origin, and those that are periodic. We'll see these definitions again in the next video. Third is the concept of cross-correlation, which tells us the correlation of 2 signals at different shifts. And fourth is the concept of autocorrelation, the cross-correlation of a signal with itself. In the next video, we'll talk about GPS signals, the information they contain, and how we decode that information.